Hello, welcome to the stream. It's another Sunday, a little bit rainy and overcast today, so it's probably going to look, the stream video is going to look a little bit more garish with my lighting, but we are going to resume where we pick up where we left off last week. So last week we were in the situation where we needed some type information to hint to the register allocation whether a variable was going to be a stack variable or one of the roots on the heap. And we didn't have that information. With the exception of a few places, we'd basically thrown it away. So all of the type inference was done right at the beginning, and we made sure that all uses of variables had the right type. But we didn't propagate that into the middle layers where we could annotate like generated variables that are used for some transformations with their types. And we didn't have a complete understanding of where various vector types or tuple types are going, and so this made it challenging when thinking about the only place that we had kept that information was in the allocate statement. In the allocate statement, it's fine to keep it there because you need that type to know how to format the tag of the allocation, because all of our heap allocations are tagged types. Then that vector type is going to have at the lowest bit a 0 that is used during garbage collection, and then there's like 6 bits for the length of the vector, and then 50 bits which are single bit flags for whether this contained thing is also a pointer. And then the top, I think it's like 7 or 8 bits is unused, but let's see, that would be 7 bits. The top 7 bits is unused. But okay, so where I'm going with that is we needed it there in the allocate statement, but once we moved on to something else, that information was gone. Like we didn't know that a particular variable that was assigned from an allocate statement had a particular type. And so if you moved it, if you like copied that variable into some other variable, now you have a layer of indirection there, which may be a valid transformation, right? We often have to do things locally, like without global knowledge. So sometimes you like allocate into a variable and you fill in all the fields of that vector, and then you forget that variable exists because you moved it into something else, and that something else doesn't know what type that thing is, or at least it doesn't carry that information with it. So we need to make sure that when we do this this allocation, and we're trying to assign registers or spill onto the stack or spill onto the root stack, which is the more important thing here, we need to know what that variable is, and like what type it is. And so last time we started plumbing more deeply into our middle layers, that information about types, and more importantly, when we get to the select instructions phase, which is where some of the most significant type erasure happens, it's like where you take a Boolean and you turn it into a 0 or 1 in the assembly code, right? We still need to know what that is, and we are doing the same with integers, and now we'll have that type information with vectors that we can propagate up. So we were in the midst of doing that. And I'm going to flip over to the coding, and we'll get started on that, because what I want to do today is finish out this type propagation and then get to the actual register allocation algorithm, because it needs some minor updates. But if we have this type information, we can inform it better, and that's really important. So, all right, here we go. Okay, so last time we built this. So when we're in this C-like language, all of our primitive operations have this atomic for arguments, and the atomic is basically like, it's not another expression. It's either an immediate value or it refers to something that's been allocated on the stack or the heap. And so here's a spot where we can propagate out the type. Since we already know what this is, if we go to this definition, you can see it has an int, a bool, or variable, void, and then we have this wrapper that we added last time, which is a wrapper around. So this is a self-recursive type. So if we have an integer, we can emit the fragment of code for this, which is just an immediate containing that integer, and then we have integer t as the type. And I'm using option here because if we have a variable and we don't know what its type is, because at this section it's just a variable, we have to return none. But if it has this type wrapper around it, hello, welcome to the stream. If it has this type wrapper around it, then we can say, well, it's either whatever the inner type of this value is, or it's the t that we have the wrapper. And we're only going to add this for vectors. So conceivably, this is only going to happen when you have an annotation, this has type annotation around a variable, right? So this is what we did last time, and we were in this select statement function, and there's now that we have this this select ATM, the select atom function with the types being returned, we need to handle that. So what I'm going to do is I'm going to say, let's put this in brackets, because we're going to have to do this in a couple of places. So we're going to say let we'll say value type is that, and that's, oops, we'll say t, and then here we can just put the value in there. But what we'll do with t is we'll say option dot map. Yeah, so we're going to say option map over t, and sorry, we still have the parens there, never mind. And this is going to take the, I hate to do this, but we're going to say insert types vt. Okay, so this is going to return a dictionary, and we'll say unwrap types, because types is, I'm sorry, I need to map. I keep switching languages in my normal everyday work, so I want to say there's probably a cleaner way to do that. But essentially, what are we doing here? We're saying, okay, this select ATM is maybe going to give us a type. So it's either going to be sum with a type from our type system, or it's going to be none. If it's none, we just return the empty types dictionary, right? That's what this option unwrap is. But if it's sum, then we want to insert that this variable we're assigning to has that type. Okay, and then we're going to go down and update the rest of these. So here we know this one is simple types, variable, and this is integer t, because we know that this call to read is going to return an integer. Okay. Okay, and neg q is only valid on integers, so we can do that. Again, this information is not necessarily as useful as the stuff for vectors, but we're going to go ahead and put it in there anyway, and then we'll have, the goal of this is when we come out of this phase, we'll have a dictionary for the entire program, like all the variables declared and all of their types. At least as many of them as we can infer at this phase. So again, here we've got this issue. So we're going to have to break that out. I said type T, select ATM. Except this, I'm sorry, this needs to go outside there. Okay, so the interesting thing here is that we know that this is since this negate has to be an integer. Otherwise, that would not have type checked. So I wonder if we just ignore that, but let's go ahead and do what we did above, right? So we're going to go t option.map. And here, I may make a note as we do this. I'm going to use lazy unwrap. This is going to be insert types v integer t. I'll make a note here that's like negate operator only takes integers. The other thing is that this is regardless of what this is in here, like if you think about the negate operation as just an operation on this this value, it's going to basically be an integer after this point. So we'll say and returns integers. And I think I want to move this up here. So like we should have, this should be an integer, but if it's unknown, like if it's just a variable in there, even though we've taken care of this case. Oh, so this case is if v and v1 are equal, right? Okay. So we need to go down and do this in every one of these clauses. So let's just get going to it, and I'm going to cut down on the explanation a little bit. basically this. Right, so this is just this is an optimization. All right, if you have a variable and it's the same variable, so if you're doing like a equals a plus 2, or a equals 2 plus a, then this is an optimization, meaning we don't have to. We can just apply the assembly instruction to that existing thing. We don't have, this is what that optimization is. And how, here's the more general case down below, right, where they're not a variable that you're being assigned to. So if you have like a equals b plus c, then you would go to this clause. Okay. So again, I'm going to pull this into here, and we're going to do too many commas there. Okay, and this is going to be ATM, and this is going to be for A. And then so apologies, this is going to be a little bit tedious, but we're going to get there. And, you know, here's a case where these should both be integers. But they are not. They're not necessarily, or at least we don't know. So what we're going to do here is we're going to go ta option.or tb. So that's going to, you know, if ta is populated, which we think it should be an integer. It might be a variable, we don't know. And it, you know, or tb, if it's an immediate value, then we'll use that values type. But if they're just both variables, then we do this business. Okay. And then I think we've got basically the same stuff to do down here. So I can't really copy that easily, but there are only so many binary operations here. Now we could potentially just throw, in these cases where we know that this has to be an integer because minus and plus and so forth only accept integers, we could just throw those away and say that, you know, we'll just put integer t into the dictionary for v. I'm just trying to be a bit principled about it, and it's also possible that, oops, it's also possible that this may find some bugs if we did something wrong. So and this is exactly the same as up here. Yeah, this. And this one is going to be the same as well. And this one is going to be the same as what we did above. So again, this is kind of mechanical. But it's not a factor, or it's not a refactor I can actually automate, I don't think. Because there's too much structure in here. This is a Okay, and we're missing something. It's making the formatter not rejigger all of my code. Oh, there it is. There we go. Okay, so here I can just replace that with A and B. Okay, let's make sure that all these clauses with minus are correct. Okay, so there's the last plus. So minus where you're assigning to the variable where they're equal. Okay, we've got the atomic there. And then we say it's integer t. Okay. And that was on B. And this is on A. And we've got basically the same thing. Okay, and then here's the two-headed one. And that looks fine. Okay, so for this one, again, we're going to have to do the same sort of refactor. For not, we expect that this is going to be a Boolean, right? So here's a case where we do our option.map, right? This is, we want to insert var and t. And we'll do lazy unwrap again. And this is going to be insert types var boolean t. Because not is only valid on Boolean types. Okay. So comparison, we're going to have to pull that out. The interesting thing here is I think in this case we can throw them away. Because if we are assigning to this variable, the arguments to comp don't matter. Their types don't matter. So what we can do is say that this variable is a Boolean, right? Because if we're assigning the value of comparison to it, that's going to comparison returns a Boolean. Okay, so read statement doesn't assign any variables. It's just like read something from the console and throw it away. So there's no types injected there. We'd already handled this case because the allocate statement has a type attached. We don't have a type for global variables. They're all pointers. If we're assigning vector length to something, then we can say that we know that vector length returns an integer. Okay. So there's a problem here. That we need to get to, and V is an atomic. Okay, so we should, let's remove this let assert, yes, we expect it to be variable. But what this is going to be is actually this. Select ATM. Right, so this will, if there's a wrapper here, actually at that point we don't care that it's a variable. So we'll just throw it in there, right? Like we expect it to be a variable and we don't need the let assert. So now the question is, we need something to get from this type, get the type at index. So there's a question about, do I do this here in my mind, or do I do it in the top level? Remember here we did this stuff last time, that when we're referring to a vector ref, or we're setting a field on a vector, it like does this maybe wrap with type thing. Okay. Let's look at our type definition. So our type can be in the integer, boolean, void t, or vector t. So what I want to do is make a function here. Okay, that's all about interpreting. And we have type checking. Okay, so that's checking whether indexing into the vector is correct. Okay, maybe wrap with type is what we added last time. Let's make a pub function which is type at index. And this is going to take a type and maybe return an option of type. So we're just going to say none is the default. And if we say that this is a vector, then we're going to do list what do we have? Sorry, that's doesn't need to be up. Okay, so I have the standard lib up here somewhere. Yep. So list yeah, there's no at, so I probably need to not partition. I think it's just take or drop. Okay, so if I wanted the thing at index 2, which would be 0, 1, 2, right? You can drop that same number and then take the first. Okay, so we're going to do fields, and this is going to take index as an int. Drop index, and then we're going to do first, and then we're going to say option from result. Okay, so oh, I'm sorry. This needs to be not vector, but vector t. Then it'll be correct. Okay. Okay, so what did we do? We said we're going to take the fields that are in this vector, drop the first n. So for index 0, drop 0 will give us back the original list, drop 1 will give us back the tail, and so forth. And then we're going to take list first, which can return an error like this is an empty list. We should not be, at this point in our program, finding anything that is improperly indexed. That's checked at this level, but from a type perspective, this is the safe thing to do. And then since we want this to be an option of a type, then we can turn that result into option from result. We can turn that result into an option using this option from result function. Okay, so if we do we're going to say let t is type at index, and then we'll say vt and n, right? So this is, but this is actually going to be, we'll do option.map, right? So vt doesn't return anything. It's not option map, it's option then. Yeah. So option then is like bind, monadic bind. VT. Okay, so then down here we can say t option map, and here it's just going to be right. So if we have the type of this field that we're extracting, we can do insert types var t. If we don't have it, then we'll say option unwrap, and we don't have a reasonable thing, so we'll just unwrap with the empty dictionary. Okay, so that was probably one of the harder ones, but it's one of the ones that we wanted to handle. Let's say that the index into this vector contains another vector. It would be valuable to know that this variable contains a pointer when we do that move, right? So cool. Love it when a plan comes together, so they say. Okay, so for here, we don't have a we'll call it that. We don't care about the type of the vector at this point. And we know that, like previously we asserted that this should be a variable, but if our type checking is correct, then this will have a has type wrapper around it. But what we want to get back is the variable. So it's fine. We can throw away the type there. We need to pull this out. And again, we don't care about the type of that. And the thing is, we're not introducing any new types here, but we know that vector set returns void. So we can say var is void t. And we'll have a similar thing down here, except that yeah, let's just do this, and we don't need any. This is a vector set statement. It's not assigned to anything, so there's no new types introduced. And collect does not introduce any new types. So I think that's everything. Let's see what's wrong here in our buffer. Let's go down here. Oh, okay. So we also have to deal with tail position, and it's going to be a similar thing. But you don't assign to anything in tail position. Right, so we already handled merging the types in this sequence one. But if you're on a return statement, you're not going to introduce new types. Okay. I convinced myself. Right, I think there's this assertion may not hold longer term, but we have made the assertion that our program will always return an integer regardless. So we can safely assume that this atomic is an integer, but we don't know for certain. And it also doesn't matter because we're in return position. Oops, in tail position, right? There's going to be no new variables introduced in tail position. So hopefully this will be straightforward. And again, the variable, oops, the variable, there's no variable necessary here if you're just adding two things because the result is going to go to RAX either way. Same thing here. You'll note here we have that panic. That's probably not necessary, but that's basically just this. Okay. Right, and go-to can be in a tail position if it's a block that's not the last block in the program. So we just need to do this, And this one is just asserting that your branches always have gotos. Just a little bit of a sanity check there. Now, what we could do in some of these cases where we're throwing away the types is rather than do this pattern match, we could wrap these with like pair.first. I'm not really fussed about either way. We're going to replace this with vec. We know it has to be variable, but there's no point in asserting that here because we may have a has type wrapper around it. We should, actually. So this is going to look fairly similar to what we did above, except that we're going to throw away the type because we don't care. It's not being assigned to anything new. Now, we don't need the let assert. And here we do vec. Now, one thing that we could potentially do is, because this is indexing into the vector, we could say, we could check that the type there is an integer, but our type checker should have handled that, so we don't need to put in that check. Okay, so then the other cases are things that we should not care. Okay, so let's go back up to the top. I want to make sure that when we get this, right, so this is folding over the blocks in the C program. And we did this last time. And we're going to pull out the existing blocks and their types. So then we do select tail on the contents of the current block, right? And there's potentially new types introduced. And we construct an x86 block for that. And then we are merging the new types that were potentially introduced. Now there should be something here. Maybe there's a for dictionary. Maybe there's a merge where you can. I want to put in a assert, make sure the type of the index is in. Yeah, I guess we can do that. Hi Xavier, glad you could be here. Yeah, that is a good idea. So let's go ahead and do that. And you were referring to this tail position vector ref. Yeah. So we'll do let assert sum l dot integer t, and that's going to be we'll do option like we did above, then type at index. I think, yeah, we're gonna have to do vt. That is a good idea. I mean, it's a little bit. I would almost rather do a. I mean, a let assert is fine here. I would almost rather do an explicit panic, but all right. Okay? So this takes vt. All right. Assert a contract require. Yeah, I mean, the let assert is like not exactly a macro, but you could think of the let assert as looking something like case and then right hand side, and then if it matches left hand side, then you do nothing. Otherwise, you do panic as blah. I don't know. That's basically what let assert is. So yeah. Cool. Good call out, Xavier. Thank you. Okay. That's pretty good. So now we'll have this type information in this new field in our x86 program. Yep. And again, that's going to have the inference graph that we have not populated yet. Okay. Interference. Excuse me. All right. Now we have. Let's run the tests. Yeah, we're going to have a lot of problems because we have type information everywhere now. So probably what we can do is, excuse me. That isn't that many failures. I think we can go back and fix that. It's a lot of output, but there's not that many failures. Okay, so let's go to explicate control test. And that's vector ref test. All right, okay, so the C program, yeah, the problem here is that these are not getting their types around them. So what we would expect here is has type, right? And that's going to be this because we've assigned to it. And vecnet 5, I don't think has it probably will. So we'll probably have this, but it's going to be unwrapped one level, right? Okay, and then let's see here. Unfortunately, I'm kind of feeling the size of the text here. I can't see as much as I would like to. Some of this comes down to like our order of blocks. Yeah, so we've got has type wrappers on there. vecnet 5 is not wrapped, so that's interesting. Okay, so temp 7. That does not have a type around that variable. The interesting thing here is, like, I would like that to have a type around it, but let's see if I don't think temp 7 ever gets its a type wrapper around it. Again, these are generated, I believe they're generated by remove complex operands. But remove complex operands doesn't necessarily preserve that type information for the new variables. So maybe this whole thing was in vain and we should have done it at a higher level, like explicate control. And it should just put it in here because we're not really using that. I'd have even forgotten what that was for. Let's see. So a C program, it's just a mapping of strings to strings. I don't remember what this was for. Here, can we find all references? No. All right. Because in this situation, I would hope that this would have the has type, but I guess if the and when we're doing select tail, we're not passing the things in. And we're not looking anything up in them either. I wonder if this is going to be enough. I think the key here is going to be, what do we get when we're producing the x86 program? Like, do we get enough types? Here's the types. We've got integer, 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 and that's it. This is a simple program. All right. Let us not get deterred. Let us soldier on. Okay, so right, so let's look for the vector set statements and possibly the vector ref statements, but I don't think the vector ref statements will have it. Okay, so here there's going to be vector set down here. This is going to be has type, right? And it's going to be this type. And I don't think that there's any others. Let's go down here just to make sure. So we should get this one passing now. Yeah. Okay, let's go back up to the top, see if we got explicate control. Okay, so it's still failing. Okay, this is the one we expected. Okay, so temp 8 got one. That's interesting. That's good. I'm glad. At this case, this is the return, so we're expecting that that's this type, right? Yep. See if we have any other has types. Okay, so alloc2 got one in the vector set. Yeah, so we did that. And sorry, this is, again, a little bit tedious, but we've introduced some pretty serious breaking changes along the way. Okay, so this one should potentially pass now. 7 failures. I think we passed. Okay, so let's go look at I actually wish that there were something in the language server to help with this. Maybe that's something I'll contribute in a future stream. That like you could run the tests and see what, like have it point to which tests were failing if you're using Gleam unit. Okay, so we've got expose allocation test. It's just this one test. Okay, and this is actually fairly straightforward, I think, to fix. We can probably even like hide the result and just look at the places where we would expect things to be wrapped with has type. Okay, so we expect here. Basically this, right? Oh, that was bad. Okay. Right, because this is the expose allocation phase is what injects the allocation collection and so forth. Right, so here we'll have a has type, and it'll be this. And I don't think that there are any other places, because we only added it in vector set and vector ref. So let's look at vector ref. Where are we doing that? Right, because this is our original thing. Okay, so vector ref. Let's run the tests again and see how close we are. Okay, so we have has types around these. Yeah. Yeah, so so unfortunately this is going to introduce another wrapper, right? And this is the inner vector, so it's going to have this type. And I'm going to collapse that so I can see what the heck I'm looking at. Oops. Okay, so this one has this type, and then we're going to have a has type around here. Around this one, right? which is going to be L dot vector t. Okay, so hopefully that is going to be clear enough that like this whole program is construct a vector with an integer in it, construct a vector with that vector in it, and then so we'll have a has type around this, we'll have a has type around this, so that's the inner part of the first vector ref, and then there'll be a has type on this because this vector ref has a type that is a vector as well, and it's an argument to vector ref, so we will have a wrapper around that. So you kind of see deep on the inside, we have, you know, this let, the result of this let expression is this. And so it's going to have that type on it. All right, let's make sure that inside here we're getting the right stuff. So vec_init 5 the only other possibility here that I'm thinking about as this might not be complete is that this vec_init 5 might have a has type wrapper on it, but I don't think so. Let's run the test again, and we still have 7 failures, so we're missing something. Okay, interestingly enough, this inner let doesn't have a type wrapper on that vector ref. So that's a place where it's dropped. That's interesting to know. So that might present a problem. Oops. And since it's a direct, all right, let's remove that wrapper and see if we've got it correct. Oh, I've got some extra parens there. Yep. And what did I break? There we go. All right, I need to do some collapsing to make sure that I've got this correct. There we go. The issue was in the middle, not at the end. Okay, what do we got going on here, folks? I think I deleted the wrong. And it's hard with the collapsing. I kind of want the collapsing for clarity, but yeah. Yeah, I know. It's like, you know, we wrote this by hand in a previous stream, and here I'm going, what the heck was wrong with me? Makes me think of lists. Yeah, like, honestly, paredit would fix me. I don't know if any of you have used paredit, which is a mode that you can turn on in basically any mode in Emacs, but its main advantage is that you can never type anything that doesn't have matching parentheses. And it's super useful for Lisp when you're doing deeply nested things, that it'll automatically add them, and you can't delete a parenthesis without deleting the entire expression that it contains, right? It's a pain, but it is useful. Okay, so okay, I think the issue is this. The collapsing is not correct here. So if I do this, I can't collapse that. Let's collapse that. Let's collapse that. Okay, so let vecinit 5 contains an inner let and another let. And then this vector ref. Okay, honestly, I think I'm going to have to back all of this out. Because I just made a complete mess of it. Here, let's just we're gonna, right, that's the problem, is it's like, hey, you've got some stuff in the nesting. Okay, we're gonna back this out. It's still wrong, it's still broken, but now hopefully I don't mess it up again. Okay, so what did we determine? Does this have a has type on it? One thing I would love about Gleam test is to be able to focus one without commenting out the others. But I don't know, that's not part of the runner right now. Okay. So there's actually a has type around the outer vector ref. Okay, so was the issue that we don't need this? And we do need it here. Let's get the nesting correct here. Okay, so we do have, we have vector ref, we have has type there. And this, yeah, so this next vector ref does not have a type wrapper on it. We're going to have to go down here and do some wrappers around our allocations, but those we kind of expected. So let's copy that one. And then we'll have it around alloc6 as well. One thing that I do appreciate about using Gleam for this is that these names are stable. As long as we didn't change the order of operations in our compiler phases, those names aren't going to change. Okay, we still have 7 failures. Let's see if we can figure out what's wrong. And we'll just scan and just make sure that we've got the wrappers in the right place. Mm-hmm. Okay, so here we actually have a wrapper on this variable as well. So alloc2 here. I wonder if we will have that on alloc6 as well. Probably, because that's what the type checker would probably do. No, this is just, let's see here. Oh, right, because this is in return position from this let expression. So it's like, I know what that is. I'm deep in here and you allocated that, and that's what the type is. Okay, so we'll probably have something similar down here where we're returning alloc6, right? Hey, we're down to 6 failures. Woohoo! Okay, so we figured it out. That's good. Okay, so remove complex operands test. You know, I may have gotten myself into a pickle here. There's probably some simpler way to do all this, but some side channel for this information, I don't know. Okay, we're in vector ref condition test. Okay. Right, okay, so these right, so the vector sets are going to have has types on them, like we've seen this before. Oh. We can just copy it from here. Interesting, I didn't use the L as the alias. Maybe there was something else going on there. Okay, and actually we can replace this here and here because this is a 2-element vector. And then there's probably, since this is the return, it's probably going to have that here. Oop. Sorry. Right, our atomic is in the has type goes in here. So we can replace this with this. Now let's make sure that there's nothing else. So we might have let's start here because I know that it's going to be there. We might have. I've messed up the syntax. There we go. Still broken. Oh, we've got multiple problems there. We need it here, and we're missing it there as well. Okay, okay. I was like, why is it not reflowing? That's why. It's probably still going to be broken because we've got. We probably have more wrappers. Okay, interesting. It's not there. It's also not there on V1. So, oh, sorry. This is the thing that we passed in. Okay, it is on V1.1. So let's fix that. The thing is, it's going to be the same as our alloc 3, right? And then it'll be here as well. Still fail. Okay, so let's scan real quick, make sure we didn't miss anything that was obvious. Okay, the if let temp.for from vector ref, right? So that the var has type there. Oh, but atomic var alloc 3 is not returning. It's not wrapped. That's interesting. I wonder why that would be the case in our other program, but not in this one. Okay, we're down to 5 failures. We're getting there, folks. Hang with me. We can do this. Okay, so select instructions. This is the thing that we are actually working on. All right, we don't need Gleam IO right now. Okay, so the base select instructions test. So what we will have now, though, is because we've used these, or we've generated these variables, we're going to know what types they are, and so this should be straightforward to fix in every single one of these that fails. Because before we didn't have this. So we know x.2 is integer t. X.1 is going to be integer t. And y.3 is going to be integer t. Okay, let's see if it fixes that. 4 failures. Yeah, so this is going to be straightforward to do, I think. It's just going to be as many as we can do without looking at the result, the better. Okay, there's just one temporary variable. should be easy. Okay, so this one we have temp1, temp, and temp2, both of which are integers because they take from read. And that's basically it. Remember, a lot of these early programs that we wrote tests for a compiler, they are pretty simple. Okay, here, say types is dict from list. And this just has one, right? X.1 is a void t. Read statement. Okay, here we have x is getting a value, so. And if any of these are wrong, that'll be interesting to dig into. But I think that if we go through all this, for the tests that we have already, okay, we don't care about the compute tag. That's nothing new. Okay. So here, we aren't looking at the types, right? But I think that we should. And I'm going to do let's do we're going to get, for instance, let's say Alloc6. This is the same program that we've done before, right? We'll say that should exist in there, and we'll say it should equal and we can actually look, let's look at, yeah, let's get remove complex operands, because that comes before here, and we have some types and things. And this is the same program we're testing through all of this. You know, it's this, not this one. No, let's look at expose control or explicate control test. Right. Yep. Split down, please. Okay. So this is the program, right? And we should expect to get this in here. Okay, and we're going to do some other ones similar to that. So we should find Alloc2 in there, right? And you know, Alloc2 should have this type. Okay, and then we should also have some of these temporary variables like, you know, temp8. and this is the same as alloc2, right? Now I could do this as let's explode the entire thing, but I mostly want to make sure that the types that are in our syntax tree here of our intermediate form, those get populated into the type list. And honestly, let's do, we're just gonna print it out. Okay. And then we'll make sure that, okay, so we do have a failure there. We got some variable void t, so these throwaway variables. Okay, so alloc2 was correct. alloc6 is in there. temp2 and temp5 are in there. vec_init is in there, but temp8 is not. Interesting. So it's possible, given that our other things passed, it's possible we missed a spot. I want to make sure that we have, and I don't know, it may not make a difference, honestly, but I want to make sure that we have a enough information that our register allocator can deal with. So let's go back and look at select instructions and see if we can't find the appropriate place. So there were some places that we were throwing away. Or it's possible that the issue is we're not getting the right wrappers. There's another possibility here that has just occurred to me, is that if we have a variable that is wrapped with a type, and it is not in return position, so to speak, like this. So like in this example, we're assigning to v, whatever v contains, the value of this atomic expression over on the right. And we're using the type thingy that we did before, where if it has the type wrapper on it, then we'll use that to populate this. Or if it's of a simple type, then that'll be returned. The problem comes down to when you have variables in argument position, and that would only happen, it would only happen in these vector ref or vector set things. But if we know interesting that this, like, we have the type information here, this becomes, move it. Move the known vector length of this thing. That would be nice. Okay. So, for example, here, it's going to be a variable, right? We could probably do a let assert here like we had before. Which means that we can go right, and then we can do stuff like except that's a we need a way to take advantage of that. Like, because this is the type of the variable that's being assigned. And I don't think that okay, I think we need to do something like option then and this would be VT map var name T. I'm sorry, this is option map VT. And just to be clear, so it doesn't, there is shadowing going on here, but maybe then is the wrong thing here, because we probably want to capture this type even if, well, here's the irony though. Like if T is sum, then VT has to be sum, because otherwise we wouldn't have, yeah, so then is fine here. There's probably something else that we could do here, like make a list of these two. I think this is fine. We're gonna have to do this again. getting ahead of myself. I need this, right? I hope this is clear enough to everybody what I'm trying to do here. Okay. And can we rename symbol vec name? Yeah, okay. So in this vector set thing, we want to make sure that we're capturing types at more places. And we'll do something similar down here. We'll do that. We're just trying to get as many places as possible. We'll do this, basically. Too many pipes. We're trying to get as many of these places as possible where a vector might be involved to extract its type, and I think that this will help. We need to look at select tail as well. And we can do, I don't think our vector length ever returns this, but and we'll do, okay, so we've got it here, right, because we were trying to get the type at index. And this is just to assert that it's an integer, right? So, again, just more places if we have the type that we can do. I'm sorry, it's a VT option map. Okay, and I think that's all the places. Yep. Let's scan real quick, make sure that there's not any additional things here that we can. We could probably look at if A and B are variables in these things and add integers. I don't think that that's as important. It really comes down to, we expect these to be variables at this point. Oops. And so the let assert there is a little bit of a sanity check. Let's see. Okay, so now, oh, cool. So we are getting more, I think, than we did last time. No. Oh, no, wait. So we got temp8, right? We got temp8 in there. There are some other variables that are not, and I'm not certain whether this is going to be a problem yet. Okay, at least with our stuff passing, it would be a good time to make a commit. More extensive type information from select instructions. This is like a massive change, right? And I just recalled one thing that I need to do that I have not yet done, because we are running 1.13 of Gleam here. So this is update test workflow to Gleam 1.13. That's what we compiled with, and it was probably broken. Okay. So it's time to look back at the book. The whole reason we came here is that we want to know tuple type variables so that we can spill them to the root stack. Root stack is separate from the call stack, right? The root stack is a stack of pointers, and these are it's like the root set in any garbage collection scheme, right? That's exactly what we're doing, except that we're not explicitly looking in registers for those. They have to be on the root stack. There's a question in my mind about how that root stack gets popped when things fall out of use, because they can be returned, right? So there's some lifetime analysis we're not doing, and I'm kind of like, is this gonna work? Okay, so if a tuple type variable is live during a call to the collector, it must be spilled to ensure this is visible to the collector. So we will look at liveness analysis, right? Let's check. Okay, so the latter responsibility can be handled during construction of the interference graph by adding interference edges between the call live tuple type variables, right, and the callee saved registers. Okay. It says they already interfere with the caller save registers. So going back to here, what are the callee save registers? RSP, RBP, RBX, right, so these, and then R12 through R15. So it's saying they already interfere with the caller save registers, right? Okay. They're saying the type information for variables is in the program form, so we recommend adding another parameter to build interference function to communicate this associative list, which we've represented as a dictionary. Okay, the spilling of tuple type variables to the root stack can be handled after graph coloring in choosing how to assign the colors to registers and stack locations. Okay. So one thing they said earlier in the chapter, which I think I need to go back to, yeah. Um, and where was it? I think they were saying, right, so R11 is going to be used for dereferencing into vectors. And they spoke about, I believe it was R15, and R15 is getting right. Okay, so they use a dedicated register R15 to store the pointer to the top of the root stack. Right, so R15 is not available. And note, yeah, okay, so it's basically saying these are not available. And the negative values there, I forget exactly why those were negative. But they wanted us to start with 0 when allocating. As long as it didn't conflict. Okay. All right, so we know that it's going to be an R15, so there's going to be a conflict between R15 and basically everything in the program, and R11. But let's look at build interference, because I think that's where the key is. What's this warning? Oh, we're not using that yet. Okay. Okay. So build interference. Here we need to change this to x86. Oh, it is already x86 global. Okay. So the conflicts is the interference graph. And I thought that there was something we did. Okay, so we need to look at uncover live. I think we've already done that. But I don't think, yeah, so it's just going to get the live, it's going to create the live set, the live before and live after, right? So build interference. So we look at determine conflicts. Right, so this is taking all the list of instructions and applying the different rules to them. The thing that I'm not sure about is whether we need to okay, so we can pass to determine conflicts, I guess. The types of variables. So let's do we'll say types is a dictionary from string to l.type, and okay, so now it's saying it's not used. That's not a problem. I think that we need to pass the types into these individual rules as well. Let's look at rule 1. So rule 1 is like you're moving from source to destination. And these are the live variables, or live locations, because locations can be variables or registers, right? So add locations just adds nodes to the graph. Okay, so an add conflict would insert an edge between two locations. Right, so I think I need to pass these types into the rules, and then we'll possibly use them. Okay. We're going to figure this out, folks. It won't be so bad. Okay. So the interesting thing here is that I don't think that rule 2 requires the types. Just rule 1, because rule 1 is about moves. And okay, so we add interference edges between the call live tuple typed variables and the callee save registers. Okay, so I don't remember the exact reason why this is. Maybe we can think through it, and then we'll. Right. So this is we're folding into the graph. So we're updating the graph basically over the live set. So if the live set does not contain the source, or rather, if the location so the location from the live set is not the source, and it's not the destination. Okay. So if it's not the source and it's not the destination, these are sets, but they really just contain one item in them. If it's not the source and it's not the destination, then, so basically take the contents of this destination and put it in conflict with that location. So the source will not, if this location is the source, it won't be in conflict with D. If it's the destination and it's live, it won't be in conflict with D. But anything else in the live set will be in conflict with it. The other thing, excuse me. Actually, maybe the part that I don't know is, do we really need this? Or should we be doing it as an initialization step up here? Because if it's already in there, right, we can add it to the graph. I'm trying to remember where we added all of the registers to the graph. I don't think that we do. Yeah. Yeah, let me back this out a bit, because I think that maybe what we can do rather than doing it here is just make sure that we're going to make sure that I'm sorry, this is going to take and I'm just going to name it G because I don't want to, it is the interference graph, but I want to do we're going to add locations. Right, so that's going to be the variable. Except we don't need to do that. Maybe what we do is we go case t, and if it's anything other than a vector, we don't do anything. Okay, but if it is a vector, then we add the location. And then we need to add conflicts, right? And I think that maybe what we do in addition to this we do something like this. I didn't realize for a long time that you can have module level constants, but I'm kind of like, oh yeah, duh. And then we'll say we can probably also change these. But this is actually more efficient for the checking in the places that we have checked for callee versus caller saved. It's just that what I want to do here is use that list in our little initializer here to add conflicts between, like they say here, okay, add interference edges between the call live tuple type variables. So all tuple type variables. And the callee save registers. It's making me wonder if we were supposed to special case the collect call. Or if we should just go, is it a vector, then make it conflict with the call save registers. Okay. So we're going to go list fold, and that's going to be x86 base dot callee saved registers. And this is getting a little bit complicated, but our accumulator is the graph, and the register. And what we want to do is interference graph, add conflict to G between and register. Okay, I'm going to put a little note here. One of the things that this might mess up is it's not looking at liveness. This is just saying all variables that contain vectors conflict with the callee safe registers. Okay, the program output of this pass changes to also record the number of spills to the root stack. Okay, well, let's all right, we don't care about the types on rule 1 anymore. We're not using it. Okay, that's what that error was. So what I want to say here is I'm going to copy this. Conflicts must be added between callee save registers so that they are not we'll say clobbered. The only other thing that I'm thinking is that let's look at the right. So R15 is one of those. They say they're already conflict with caller, so R11. Okay, we're a bit over my normal time. I'm thinking about calling it pretty soon. There's a question in my mind about do we leave it here? Let's see if there's a test, perhaps, for build interference. Yes, there is. It's all commented out. So let's uncomment it and see what we get. We're going to have to fix this. And we're going to say x86 var if, and we'll replace those with x dot, replace those. Okay. Let's run this test. It's probably going to break. Okay, it does not. Interesting. One thing that we should do is probably make a test that includes variables or includes vectors, right? So and we'll do something similar to what we did, say like over here. We started doing this. Yeah. Okay, so we need parsed from over here. Where did that test go? Yeah, let's copy these out. Okay, and so the C passes should be x86.x86 program. Okay, so we need to import that'll solve those. Import that. Import that. Okay, and then this will be select instructions, right? And then we'll have uncover live. Do we have all of that commented out? No, it's still working. Okay, cool. And still passing. Okay, so these are the passes before build interference. So I think that we're gonna do something like, we know, for instance, that we don't care about this stuff. We only care about constructing the conflicts. So things that we want to do are like Alex 6, for example. This is location var. That should conflict with each of the callee saved variables. those others, and then we'll be able to, yeah, okay. Right, so we can do like RSP and be true, and let's dupe that, and we can say RBP, and we can say RBX and R12 and R13, 14 and 15. Okay, so this is the main thing that we're testing here. We're going to say tuple typed variables must conflict with callee saved registers. Now it is saying they already conflict with caller save registers, which I don't know if I believe that, but we can basically do the same thing. Entirely possible that this is just gonna be wrong, but the thing that's interesting about that is basically saying, I mean, I don't think that there's any registers that are not part of that set. Both of those sets. And let's find out. Yeah, okay. The problem is I don't know which line this is on. All right, well, let us comment these out. Okay, so that I do expect. The thing that's interesting there is it live when a call to collect happens? Let's have a look at some of the output here. Maybe not in there. What I'm interested in is what is the output of the uncover live? Like, what are the live sets? Because we can probably look at the output of select instructions and know. So if we're going down here, right. Again, I don't think that this is enough. Do we have pretty printing for x86 global? We do. Okay, so we could go, we could do echo. Not echo, we could do io.println. Yeah. Oops. And we'll say and up at the top here we're gonna have to, oh, cat, get off my keyboard. Okay. Okay. So let's do that in this test. Okay, so this is the program. So there's questions of you know what, something that might be neat, and we'll do this for 5 minutes and then we will call it for the day. But when we're formatting a block, I think I'd like to see the I'd like to see the live before set printed there, right? Oops. So let's do that. I believe it's hash marks. So let's do we're going to break this out onto multiple lines. So we have the label. I'm making a spaces break. Right, so if it does break it, it does nothing. Okay, and then we're going to do we're going to from string hash mark with a space. And then I want to do, we'll say format live set, which will take block dot live before, block body, yeah. And then let's make a function here, generate function. Okay, so this is going to be similar to our other things that do parenthesis. Do we have a parenthesize function here? No, we don't, because we don't usually use it. Okay, so we're going to do location is going to be a location, and that's going to be document. and then for location register, we're going to do format register. Yep. Reg. And this is just going to be doc from string name. Okay, that's easy enough. So we can do what have we done before? We've done this pattern. Okay, so let's do set is going to be set.map format location doc.concat join with from string comma space, except we actually want non-breaking spaces, and we're doc prepend I don't think we're going to need to break lines. I don't actually want it to break lines at all. Doc.append. Okay, and then this is going to have to be a set to list. Okay, so I think we've got this, and now we'll have the live set. So let's run that test. And you know, I printed it with okay, so the live before for block 1 is RSP and vec init 5, which we expect because our start jumps to, okay, wait, where's vec init 5 set? Okay. Okay, so if we know what vec init 1 is 42, that's not a vector. Let's look at the other call to collect. Right, so vec init 5 is a vector. Okay. So block 3 jumps to block 1. And yeah, like it's saying R15 has to be live before block 3. And what jumps into block 3? Block 4 does. So yeah, so you can see R15 is live before the start function, which is saying, hey, this is our root stack. So I think that's working out as expected. And it comes down to how we're generating the call to collect. Pretty cool, huh? We were able to make, and let me put a little bit live before. Put that there. And so we're getting, you know, information about the live before set at the start of each block. Pretty cool. All right, this is a good place to stop. I think that that'll be enough information to see, does this make sense for each of our blocks? You know, are we going to get the right conflicts there? Let me go ahead and commit this. We didn't quite finish this at the level that I wanted to, but one thing that I appreciate that we're able to do on this stream is gradually keep adding the things that we need to understand, is this code correct? And that's good. I feel like that's good. All right. Well, I'll see you next week, I hope. Take care.